So far we've learned how to simplify radicals, how to multiply, and how to divide radicals. So now this video is going to be over how to add and how to subtract radicals. Let's review some vocabulary that we've seen in the polynomial video. We want to add these radicals by adding like terms. And when we talk about like terms, that means we have the exact same variables with the exact same exponents. That's what we saw in polynomials. But here, we need the exact same exponents, exact same roots. Basically, everything has to match, and then we can just add the numbers in front. So, just a review from our polynomial video, when I try and add these three terms here, I can actually only add two of them, the 8x squared and the negative 3x squared, because those are like terms. 8 minus 3 gives me a 5x squared, and then the 6x I can just copy down. I cannot combine it to anything because it does not have the exact same exponent like the other two do. So this is the principle that we're going to use when we're adding and subtracting radicals. Everything has to match. They have to be like terms. So we have examples here. I have two of them. I believe that I have given you enough information to work both of these on your own. So I suggest that you pause the video and go from there. So example 1 is very easy because it's already set up into like term fashion. Notice I have the fifth root of 3x in both of my terms. Those match exactly. So all I need to do is subtract my numbers in front. So 6 minus 4 gives me 2, and then I combine the like term of the fifth root, 3x. So that one is just a one-step process. Example 2 is a little bit more complicated. I cannot add it at first, but my first step would be to simplify it using the techniques that we've learned in the past, the good pi, bad pi technique, and then hopefully at the end of that I have like terms in which I can combine. Now my root 2, I cannot do anything with it, so that's going to stay as is. So let me try and simplify this square root of 50. So let me split it up into a good pi and a bad pi. Square root of 50 does not come out evenly, but it divides by 25, which does come out evenly. And I have a 25 times my square root of 2. I can take the square root of 25 to give me 5, and then copy down my root 2. Now, that was just what happened to square root of 50. So I need to see what's happening to the rest of the problem as well. A simple mistake that a lot of students do is either lose this 9 or just don't know how to incorporate it correctly. Well, this is 9 times my square root of 50, so in every single step I can write it as 9 times that next piece. And again down here, 9 times my 5 root 2. Now I can just multiply the outside of these roots and then copy down my inside of this root here. So 9 times 5 gives me 45 with a square root of 2. And then the rest of this minus 6 root 2, I would just copy it down from step to step. So at this point, I notice if I look at my square roots, they are identical, which means I have like terms. So I can just add the numbers in front. 45 minus 6 gives me a 39 and attach my like term of square root 2. So I have my answer to example 2. Now I actually have a third example of this, but this one is quite a bit more complicated than the last two examples. It actually follows the exact same steps that we used for example 2, which is simplify all the roots completely using good pi, bad pi, and then combine anything by the subtraction here if your roots match exactly, if you have like terms. So at this point, I suggest that you pause the video and see if you can get the correct answer to this problem. So in this guy here, I'm going to focus root by root, and then hopefully at the end I can combine these. So let's start with the first one here. Don't lose that 8 out in front. Again, that's a mistake that a lot of students make. So if I copy it down from step to step, my chances of losing it are very minimal. Then that is multiplied times this here. So I'm going to already set this up into a good pi and a bad pi. I'm looking at fourth root here. The fourth root of 32 does not come out evenly, but I can take the fourth root of 16, and 16 times 2 gives me 32. A to the fifth, I want to pull out the largest multiple of 4, so that gives me a to the fourth, which leaves me with an a left over. And b to the sixth, again, the largest multiple of 4 is 4 of them, which leaves me with 2 left over. Now let me simplify my good pi here. Don't lose that 8 in front. 8 times the fourth root of 16 gives me 2, and a to the fourth, b to the fourth cancel out, just leaving me with ab, and then copying down my leftovers or my bad pi. Last step is to multiply these guys out in front. So 8 times 2 gives me a 16ab, and then I have the fourth root of 2ab squared. So that's what I get when I simplify my first root here. Now let me switch my focus to the second root, and I'm going to do it in a different color, so hopefully that helps you visualize how all these separate out. I'm going to keep my 5b out front, and I'm going to split my square root up into a good and a bad pi. 2 is not good, nor can I divide it by anything that will come out evenly when I try and take the fourth root of it. So it automatically just goes over here into my bad pi. A to the fifth, I can break down as a to the fourth times a. And b squared does not have enough b's in it to pull out a grouping of 4, so it is all bad pi. So the only good pi I had in this one is a to the fourth. Let me simplify that good pi. My fourth root and my a to the fourth cancel out, just leaving me with a. Copying down my leftovers, my 2ab squared. Now I can multiply these here out in front, so that gives me a negative 5ab. Basically, I just wrote those variables in alphabetical order. And then I have a leftover of fourth root of 2ab squared. Okay, so I've simplified my second piece completely. So let me focus on my third piece here, which I'll do in blue. Again, the same process. Don't forget to copy your AB down from step to step so you don't lose it. I have the fourth root of my good pi and the fourth root of my bad pi. So I'm pulling out the fourth root. The largest fourth root that goes evenly into 162 is 81, and 81 times 2 gives me 162. I only have one a, which is just going to go into my leftover box, and b squared, again, is just going to go into my leftovers. I do not have 4 of them, so I cannot pull them out into a good pi. Just simplifying my good pi, don't forget to copy down that piece in front. The fourth root of 81 gives me 3, and then copy down the rest of it over here. Multiply these guys out in front. So I have a 3ab. Again, basically I just rearrange it and write it in the best order. And then my leftovers are the fourth root of 2ab squared. So I have simplified my third term completely. Now I want to look at these and I want to identify like terms, which means all of my variables and all of my roots have to match exactly. So if I look at my first piece, I have an a b, a fourth root of 2ab squared. So if anything's going to be a like term, it has to match all of that exactly. And notice they actually do. They all have an a b, a fourth root of 2ab squared. So since all of that matches exactly, I just have to combine these numbers in front. Basically, I have to take a 16, subtract 5, and subtract 3. So 16 minus 5 is 11. 11 minus 3 gives me 8. And then attach my like term of a, b, fourth root of 2ab squared. So that is my final answer to this monstrosity of a problem. And now you should be experts of how to add and subtract radicals. Just remember they have to be like terms, and you might have to simplify each term individually first to get to that point.